Hey guys, this is Debmala Chakraborty. I hope everything is going good. In this video, I'm going to talk about scent in music. Uh, in my previous video, I have discussed everything you need to know about pitch in depth. So just go and watch that video if you are curious. And here also, I'll try my level best to deliver the content you need to understand the scent in detail. I'll mostly talk about the mathematical equations and the mathematical formulas because there is a lot of mathematics behind scent, okay, behind pitch and behind scent. So if you are a musician, I think this much mathematics is really required. Uh, Otherwise, you will not get the entire idea. Okay, so let's start about uh, the discussion. So first of all, let me switch off my camera. I think my screen is visible. Okay, so here in my screen, you can clearly see a picture. I think most of you are familiar with this. So this thing is nothing but a snapshot of an octave taken from a piano. Right. So from here to here, we defined one octave. So here we are discussing about the 12 tone equal temperament system or 12 TET, where one octave is divided into 12 notes. Okay, 12 equally tempered notes. So what does it mean by that equally tempered? It means that if we take the ratio uh, of any two adjacent notes within an octave, the ratio value will be same. Okay, so let me first define the notes here. So starting from C, okay, starting from C, we get here C sharp, this is D, D sharp, E, F, F sharp, G, G sharp, A, A sharp, B, and from here the same pattern will be repeated. So this is nothing but the beginning of a new octave higher than this. Okay, the beginning of a new octave higher than this, right? And for every black note, we can also define the flat. So this is basically if we go up from C, we get C sharp, and this same note is just half step uh, below the D. That means it is D flat. So this is E flat, this is G flat, A flat, B flat. I think most of you are familiar with this thing. Okay. So here, if we take the ratio, suppose we are taking the ratio of this note and this note, C sharp and C, and we are taking the ratio of B flat and A, we'll get the ratio exactly same, the ratio value exactly same in 12 tone equal temperament system because all the uh, notes are equally tempered. So before discussing about scent, I think you need to understand about some terms, that is note, semitone, tone, whole step, half step. Okay. So I see that there exists a lot of misconception regarding these terms. So you may observe that some people tell you that the tone of your voice is very nice. They may tell you this, or the tone of this guitar is beautiful. So we basically use the tone word informally to define the quality of a voice or to define the quality of an instrument. But I think from the in the context of music, it's not so appropriate. Using the term tone is not so appropriate. So why? Okay, so let me first define the note. So here you may see the labels for every fundamental part of an octave. So from here to here, we have 12 musical notes. So each of these things are known as note. And here these 12 notes have defined the chromatic scale. So we can interchangeably use the term octave with the chromatic scale. So I think the definition of scale is clear to you. The scale is nothing but some collection of different musical notes. So you have 12 equal tempered notes in 12 TET system. From here, if you take any proper subset, okay, or if you take the entire subset, if you take the subset, you will get the chromatic scale. Or if you take the proper subset, you will get something like major scale, minor scale, diminished, augmented, pentatonic major, blues. uh, a lot of scales can be defined using the 12 notes within an octave, right? So these things, or these fundamental parts which actually integrated to define an octave are known as the note. So here C is the note, E is the note, F sharp is a note, B flat is a note. Okay, these things are called as note, and collection of notes define the scale. Collection of notes define the scale. Okay, so what does it mean by whole step, half step, semitone, and tone? And why I told you that using the word tone is not appropriate to define the quality of an instrument or a voice. Why? Because when you see the definition or the formula of finding a major scale, so for defining a scale, you definitely should have a root note. You definitely should have a root note from where you start defining your scale. And from here, if you go, so you have the definition like WWH, WW, WH. So this is the definition of or the formula for finding major scale. So from root note, if we go to whole step, again whole step, half step, whole step, whole step, whole step, half step. So this thing is for finding the major scale. Okay, let's take the example of C major. C major. So here C should be the root note. C should be the root note. So from C, according to the formula, if we go to whole step, we get D. Whole step is completed. From D, if we go to whole step, we get E. E. From E, if we go to half step, we get F. From F, we need to go to whole step, that is G. G. From G to whole step is A. Whole step is A. A to whole step is B. B. And at last, from B to half step is the C. That is the beginning note for the new octave higher than this thing. So this is actually your C major scale using the formula like WWH, WWWH. But I see that some people also use this formula like tone, tone, semitone, tone, 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 semitone. So for whole step, they use the term tone, and for half step, they use the term semitone. Okay, so none of this is incorrect. Both of them are correct. This is also correct, and this is also correct. You can define as per your notational understanding, right? Okay. So what does it mean by the semitone, whole step, half step, tone? Okay. So these things are basically just the interval, just the interval. If we take if we take any two notes, if we take any two adjacent notes, suppose this and this, D, sorry, not this and this, D and D sharp. So these are adjacent note. This and this, E and F. This is, and here also C sharp. So this is also these notes are also the adjacent notes. If we take any two adjacent notes, we get basically the interval. So the interval between any two adjacent notes is known as the semitone interval. Is known as the semitone interval. Interval means nothing but the distance between two adjacent notes in an within an octave, right? So this semitone is also known as the half step. That is how many steps we are going to find a note higher than uh, the note you are at present. Okay, so just higher than, just higher than the note. So from C, if you go to just the higher note, you will get the semitone. So the distance between C and C sharp, or the distance between E and F, the distance between A and B flat, this distance is known as the semitone interval or half step. Okay, so I think this term semitone and half step is now crystal clear to you. Okay, and if we go from here to here, suppose instead of going to the adjacent note, if we go to the adjacent of adjacent note, from here, instead of going to C sharp, if we go to D, or from here, instead of going to half step, instead of going to one step, if we go to another step, okay, this interval is known as, or the distance, this distance is known as the whole step or tone. That's why I have told you that using the word tone to define the quality is not so appropriate, because tone defines an interval between two notes within an octave. It does not define the quality. It does not define the quality. Okay. So I think now your understanding about semitone or half step and tone or whole step is clear. I think now it's clear. Okay. And in the similar way, G to G sharp, G to G sharp, we have the semitone interval. The distance between G to G sharp is one semitone. So instead of one semitone, if we go to two semitone, so this distance, okay, from G to A, from G to G sharp and G sharp to A, if we sum up this distance, then we will get the whole step or tone interval. Whole step or tone interval, right? So these terms are now clear to you. Now I will discuss about the same. In my previous video, I have told you that what do you actually mean by the pitch for a particular note? The pitch for a particular note is basically the fundamental frequency of that note. Okay, fundamental frequency of any note is known as the pitch for that particular note. Basically, when we hit a note, when we hit a note, suppose with the help of our voice, we are singing a note. That note does not produce a single frequency. It produces the fundamental frequency along with some harmonics or overtones. So here, at this fundamental frequency, our vocal cord vibrates. And these harmonics actually define the tone color or quality, or we known as the timbre for a voice. That's why I have told you that it is not recommended to use the term tone to define the quality of a voice. A voice quality should be defined by its tone color or timbre. So you can say here that the timbre or tonal quality of your voice is very nice, or you can say that the timbre of this guitar is very good. Okay, so these harmonics are basically nothing but the integer multiples of the fundamental frequency. I have discussed everything in my video regarding pitch. Okay, so from this harmonics we get some frequency regions where uh, we get the boost in frequencies. So these boosted frequency regions are known as the formants. Okay, these boosted frequency regions are known as the formants, and for this kind of frequency boosting, which is actually uh, done by, or which is actually happen due to the cavities in your mouth or your nasal, or for an instrument we see that the portion, okay, where actually the hollow portion of an instrument, it actually uh, define, or it actually what we can say that boost some frequency regions in the harmonics. Okay, so for due to these cavities in an instrument or in the vocal tract, okay, so vocal tract is basically the collective uh, things. So our cavities in inside the mouth, inside the throat, everything is collectively known as the vocal tract. So due to these cavities, some frequency regions are get boosted. Okay, and for that phenomena of boosting the frequency regions, we uh, get the resonance of an instrument, or resonance for a voice. Okay, so resonance actually happens due to the harmonics or overtones, that is the extra frequencies get produced along with the fundamental frequency, right? So everything I have discussed in that video, please go and watch. If you are curious, you can learn a lot from there. Okay, so now I'll discuss about scent. Why we need this thing actually? Where is the requirement of this thing? Without this, what problem can happen? Okay, so just take an example first. Suppose you are hearing a note with fundamental frequency 200 hertz. Okay, and you are hearing another note with fundamental frequency 400 hertz. Suppose from here also you have increased the frequency 10 hertz, you will get 210 hertz. And if you increase the frequency of this note uh, by 10 hertz, you will get 410 hertz, right? But in our ear, uh, the perception of this increment is not uniform. So from 200 hertz to if we increase 10 hertz, we will get 210 hertz. So from 400 hertz, if we go to 410 hertz, we will increment it as uh, 10 10 hertz, like, right? So this is the same quantity or the same value, but the perception may not be uniform. Okay, because human ear is not based on the frequency difference. It does not hear the frequency difference, like suppose a frequency is f2. F2 is the higher frequency and f1 is the higher frequency. So human ear cannot perceive this thing. The frequency difference cannot be perceived by human ear. It actually hears the ratio, the ratio. Okay, that's why our hearing is kind of logarithmic hearing. We don't hear the uh, frequency difference by subtraction, by subtracting, or by adding the frequencies by sum up or subtract. Okay, but we hear the frequency in the ratio, in the ratio. That's why our hearing is the logarithmic hearing. And here we need the scent. The term scent is actually needed here to define our hearing. Okay, so let me first again take this thing. As I have discussed that from here I'm not uh, doing the label again. Okay, from here to here we have one octave, right? Suppose uh, the frequency of this node is 100 hertz. Just assume, okay, the frequency of this note is 410 hertz. Okay, it may happen, but our ear does not hear the frequency, right? Like okay, this is 100 hertz, this is 410 hertz. Okay, our ear always hears the frequency in terms of ratio, in terms of ratio. So in a 12 tone equal temperament system, we have 12 equally tempered notes within an octave. Okay, and where we get every note's distance is just a semitone. Okay, so we have basically 12 semitones within an octave. So semitones is nothing but they are just the distance between two adjacent notes. Okay, this is a semitone interval. Here, this is a semitone interval, and also this is a semitone in interval. Okay, so within an octave, we get 12 semitone intervals, and we use the term scent to actually measure measure very small pitch differences accurately. Okay, and it's uniform. Suppose here you are here in this note. If you get uh, the plus 1 cent in increment from this note, uh, you will get the same perception if you are at this note, and from here also if you increase this by 1 cent, the perception will be equal, because the ratio between the adjacent free frequencies are equal. Okay, so what is basically a scent? Let me first define. So scent is nothing but a unit to measure small pitch differences in the way our ear hears it. Okay, that means it actually defines the sharpness or flatness from a note. So I think if you are into the music, you will definitely hear the term perfect pitch. Perfect pitch. So perfect pitch means 0 cent. 0 cent is the perfect pitch for a particular note. Okay. So here Again, I have to take the image of octave. Here, in the 12 tone equal temperament system, each semitone is actually divided into 100 cents. That is, so we can define that one semitone interval equal to 100 cents. That is the distance between any two adjacent notes within an octave is 100 cents. 100 cents. Okay. So if we are, suppose we have the frequency of this note is 100 hertz. So if we are at 0 cent for this note, so we are at this intended frequency or fundamental frequency, which is the perfect pitch. You have hit the perfect pitch for that particular note. Okay. So here this distance is also 100 cent. From here to here, this is also 100 cent. Here to here, this is also 100. This is also 100. Okay. So each semitone, one semitone interval means 100 cents. 100 cents. Okay. And where 0 is your perfect pitch, suppose take up the number line, the example of number line. So cent is basically defined by limiting your number line. Your number line can be from 0. If we go to the positive side, we'll get the positive values like +1, +2, +3, +4, okay, up to in infinity. And in the negative side also, we'll get up to in infinity. But for cent, from 0, we'll take up to 999. And here, this is also up to 99. So just take the positive side as sharp side, and this is the flat side. And here if you are at 0, you are at the perfect pitch. You are at the perfect pitch, right? I think this is your number line, and if we limit this number line, we will get the cent division between uh, two semitones, because here is also a semitone and here is also a semitone. So one semitone is 100 cents apart. Take the example of C to C sharp. There exist 100 cents between them. Okay. So from here, we have to define that if we uh, are a trained singer, if we are trained vocalist, okay, that plus or minus 1 cent from a note, if you cannot hit the perfect pitch, uh, and that plus minus 1 error is not so much. Okay. So this is actually tends to your perfect pitch. Okay. Tends to the perfect pitch. So for the uh, audiences who are not actually trained, so plus 5 to plus my minus 5 cents is basically the comfortable region. And beyond that value, in the sharp side or in the flat side, uh, may change that okay, you are going out of tune. Okay, you are going out of tune. So, and if you go to plus 100 cents from a note, you will arrive to adjacent note. Suppose you are at C, you are at perfect pitch C, so this is 0 cent. So if you go to plus 100 cent, you will reach to the C sharp. And if you go to suppose 0 plus 15, plus 15 cent or beyond the 15 cent, you are completely out of tune for that particular note. Okay, so this thing comes from the logarithmic hearing pattern from uh, our ear. Okay, so and here is also one thing I need to mention, that suppose from this C to this B, we know as the octave, one octave. And from here, this is just the beginning of a new octave, beginning of a new. Suppose you are at octave number is 4. So this is your C4. This is your C4. When this octave gets completed, you have shifted to the new octave, that is higher than your C4, and just the next octave from C4, and this note, the starting note, will be C5. If the frequency of this note is suppose F0, then the frequency of this note will be twice into F0. So one octave doubles the frequency. Suppose here, you are here at D4, you are here at D4. So the frequency of your D4 suppose is F5. So the D5 frequency will be twice into F5. That's why we define the distance between uh, two frequencies with the help of the logarithmic formula. And one octave basically doubles the frequency. One octave doubles the frequency. That's why we take the base for log as 2. Okay, log base 2. Suppose your higher frequency is fz and your lower frequency is fy. Okay, so fz by fy. This will give you the distance between two frequencies, where fy is your lower frequency and fz is the higher frequency. So you can clearly see that we are taking the ratio. We are not taking the distance formula like fz minus fy. So from if you calculate the distance in meter from here to here, suppose from 100 to 50, okay, so 100 minus 50, you are at the location, and from here to here the distance can be calculated as your destination, and you are at your pickup. But in the music, due to the logarithmic hearing pattern, we don't calculate the distance between frequencies by subtracting the higher frequency, uh, by subtracting the lower frequency from the higher frequency. It's not. It's actually by taking the ratio of higher frequency and lower frequency. Okay, this will give you the actual uh, raw distance. Okay, the actual raw distance between two frequencies. So from the definition of scent, it is clear that our voice, or some Indian instruments like sitar, or you can take the violin. Okay, I'm not sure that whether violin is an Indian instrument or not. Okay, just take the example of sitar, violin. They actually produces the continuous frequency, unlike your piano. So the smallest frequency distance in your piano is a semitone. A semitone in interval is the smallest frequency distance. So here this is your piano, and here the frequencies are discrete. So the smallest distance is the semitone interval. The semitone interval is the smallest distance between two adjacent notes. But the definition or the term cent is telling that the frequency uh, can be less than a semitone. The distance can be less than a semitone, right? So from here, it's not the lowest distance. The semitone is not the lowest distance. We can divide a particular note into some number of cents. For 12 tone equal temperament, we uh, actually divide it into 100 cents. We actually divide it into 100 cents, right? So each cent is basically get incremented by +1 or decremented by -1. So cent increment from 0, the increment means the sharp portion, the notes are getting sharper, and this means this is getting flatter. Okay, so this portion is for flat and this portion is for sharp. So these things actually, voice, sitar, violin, these kind of things actually produces the continuous frequency, not the discrete frequency like your piano. Okay, you are here, so just press this note, you will get C. Then press this note, you will get C sharp. Here is no concept of something like glide, or we know as in Indian classical we tell this as meed. Okay, so no concept of meed in the uh, piano. We have we get just a staccato pattern in the piano. Okay, so after C we will get C sharp. After C sharp we will get D. After D we will get D sharp. But the definition of cent is introduced for this kind of microtones movement in our voice or in the instruments like violin, sitar, and etc. Okay, and glide or mid kind of things actually talk about the ability to correct your microtones. The ability to correct your microtones. So from C to C sharp, there exist a lot of microtones, and similarly for from D to D sharp, there exist a lot of microtones. So for microtones, we need to understand this term known as cent. Okay, so here I have discussed that the octave, one octave basically doubles the frequency. So here this note frequency is F naught, then this will be twice of F naught, right? And this is suppose F5, and after that if you take the note D, you will get that twice into F5. Okay, so one octave basically doubles the frequency. That's why when we take the uh, distance between two frequencies, we'll actually get the distance in ratio. Okay, and as we know that one octave in 12 tone equal temperament consists of 12 notes. 12 notes. So 12 notes means 12 semitone in interval. So that's why one semitone interval consists of 100 cents. So 12 semitone interval will consist of 1200 cents. So we can say that in one octave we have number of cents as 1200. 1200 is the num total number of cents within an octave. Okay, so that time we got the formula of distance as log base 2 fz by fy. Now it's time to scale this value because uh, suppose your one this frequency is one octave apart. So here you are at C3, and C3's frequency, let's take it as 100 hertz, and here you are at C4. So your higher frequency is C4 and your lower frequency is C3. So this is just take the value as 200 hertz. So 200 by 100, the ratio is 2. Why 2? Because one octave means it doubles the frequency. So when we get the distance as 1, when we get the distance as 1, we basically get an octave. When we get the distance as 0.5, we basically get what thing? The half of an octave. Okay? But this distance is not so significant to understand the fine tuning, or because we the musicians want uh, an unit to understand the fine tuning for an instrument or fine tuning for our voice. That's why we are here introducing a scaling factor of 1200 cents. So if we want to calculate the number of cents within two frequencies, that should be 1200 into the raw distance you calculated. So if we write the number of cents, it will be equal to 1200 into the log base 2 fz fy. Okay, suppose take the example, take an example of two frequencies, like your fy is given as 200 hertz and your fz is given as 210 hertz. So you are slightly higher than, so you're slightly higher than this frequency. So fz is nothing but 10 hertz sharper from fy. So what should be the number of cents? Just put this thing into the formula. So this will be 1200 to log base 2, 210 by 200. So the answer will be near about 84 cents. 84 cents. So you are just 16 cent lesser than a semitone, because a semitone means 100 cents. Our same semitone in interval means 100 cents, and you are at 84 cents. So you are uh, out of tune from this frequency. This frequency is 200 hertz, and from 200 if you go to 210, so it's almost a semitone but not properly a semitone. So it can be termed as, or it can be said as that okay, you are just out of tune from your fundamental frequency of 200 hertz. Okay, so to understand this small frequency differences, we need the cents, and this is also uniform. This thing is uniform. Now, the last thing, from this formula, we have cents equals to 1200 into log of 2 fz f1. If you just do some calculation here, so this will be cents by 1200, and this will be fz by fy will be 2 power cents by 1200, because these two will be 2 power cents by 1200. Okay, so your higher frequency fz will be the fy into 2 power cents by 1200. Here cents means the number of cents between two particular nodes. You can be given, like in your question, it can be given that you have the values for fz and cent. You need to calculate the fy, or you have to suppose you may have get the value of fz and fy. You need to calculate the number of cents in between these frequencies. Okay, or you need to calculate the fz based on cents, and if anything can be given. But one thing is clear from that: if we want to go to higher than a particular frequency, that is fy, we need to multiply 2 power number of cents by 1200 with your lower frequency you are at present. And if you uh, are here, if you are suppose at fz, and if you want to reach to fy, you need to divide this thing with this. So we are getting this formula from this equation, right? From this equation. So this is only possible for, and this is only applicable for 12 tone equal temperament system. So for 12 tone equal temperament, if you are suppose at 440 hertz, if you are at 440 hertz, which is basically the standard reference. So suppose your fy is 440 hertz, and you are given that you have to go to one semitone up, one semitone up from this note. So what you have to do? So one semitone up means that fz, and 440 hertz means this is 440 into 2 power. One semitone means how many cents? 100 cents. So 100 divided by 1200. So this will be 2 power 1 by 12. Just calculate the value, and you will get the next semitone from the 440. The next semitone uh, you want to reach from 440 hertz, the frequency of next semitone. Okay, I think now this thing is clear to you. So this kind of mathematical understanding is necessary to understand uh, any definition. You need to know about the scent, or about the pitch in depth. Okay, so I think you got the idea in detail. So now, if you have any doubt, if you have any confusion or any question at any portion of this video, you may ask me in the comment section. Okay, I'm happy to answer your queries. Thank you.